Okay, let's try this.
The temperature of a bomb calorimeter is raised 3.51 degrees Celsius when 1 gram of N2H4 is burned in it. If the calorimeter has a heat capacity of 5.510 kilojoules per mole, what is the quantity of the heat evolved? What is the heat evolved upon combustion of a mole of hydrazine? Well, we have 1 gram of N2H4, and then we can convert that to moles. Well, first we need to find the heat of combustion for N2H4, which is in kilojoules per mole, so you take 1 gram and then N2H4 and...
So let's start by writing down what do you think might be a good symbol for what this question is asking us.
What is the quantity of heat evolved? What is the heat evolved upon combustion of 1 mole? So they want the heat of combustion for N2H4, and then they also are looking for Q.
Are they asking for Q of the calorimeter or Q of the reaction?
Q of the calorimeter.
Maybe that's a little subtle here, but they asked what's the quantity of heat evolved? I don't think we've used that word evolved before. I guess evolved just, I'm not quite sure how to put evolved into terms. So evolved just means that the heat for that particular process. I think when they phrase it this way, they mean the heat evolved for the reaction.
Okay.
Also, generally what we care about in real life is the heat of the reaction. We don't care about the calorimeter. We're just using the calorimeter to figure stuff out about the reaction. So when they phrase it this way, what's the quantity of heat evolved or the heat upon combustion, I think it makes most sense to focus on the heat of the reaction, although that is a little subtle. What could you predict then for your answer?
It'll have to be a negative Q because the amount of heat that the reaction is giving off will be absorbed by the calorimeter.
Would you say Q of the reaction is negative or Q of the reaction is positive?
Actually, Q of the reaction would be positive because the heat is evolved.
I didn't follow that. So is this reaction here going to be absorbing heat or releasing heat? Is the reaction going to be absorbing or releasing heat?
It'll be releasing it because it's a combustion reaction.
True. So should the Q for the reaction be positive or negative?
Negative.
Negative. That was your first answer, and then I kind of pushed you out of that answer into a different answer. So your first answer was right. The Q for the reaction should be negative because the reaction is a combustion reaction. Okay, so let's continue with solving the problem.
So first we need to find the heat of combustion for N2H4. So you can take 1 gram and then 14 times 2 is 28 plus 4 is 32 grams. So 1 divided by 32 grams, and that'll give us 0.031 moles of N2H4. Now that's how many moles we have. And they give us the heat capacity of the calorimeter, but we don't know the initial temperature, but we do know that the final temperature was raised by 3.51 degrees Celsius. Maybe I'm just overcomplicating it, but since we know Q of the calorimeter is equal to capital C delta T, we can take Q of the calorimeter, that is equal to 5.510 kilojoules per degree Celsius, and then change that by delta T, which is 3.51 degrees Celsius. So Q for the calorimeter is 19.34 kilojoules, and that's for the calorimeter. So then Q for the reaction will be equal to negative 19.34 kilojoules. So that's how much heat is evolved from the reaction. Now the heat of combustion, when you combust 1 mole of hydrazine, I was thinking we actually need to know the heat of combustion for hydrazine. So we do have Q reaction, but I guess that would be it for 1 mole. So I guess my final answer is negative 19.34 kilojoules.
Now, this problem had two different questions. So what's your answer to the first question?
Negative 19.34 kilojoules.
And what was your answer to the second question?
And that's what of a mole. By a mole, do you mean just 1 mole of?
Yes.
And okay, 1 mole. I'm not sure how to answer the second part.
Okay. So the first part said, you said there was 19.34 kilojoules of heat evolved. Evolved by what?
The reaction.
What reaction?
The combustion of N2H4.
Good. Now, one thing we should say is that when you talk about the heat of a reaction, there's maybe at least there's two common ways. There's two common ways, at least, to phrase the units for that. So what would be the units for heat of the reaction that you would think of?
Heat of the reaction would be kilojoules per mole per degree Celsius.
These are the units for the heat of the reaction that you were thinking of?
Oh, heat of the reaction. It would just be either joules or kilojoules for Q. The heat of combustion would probably be in terms of kilojoules or joules per mole per degree Celsius.
You said that heat of combustion would usually be phrased like this. Units would be like this.
Yeah.
I'm not sure why you're putting the degrees Celsius in there. So I think you're probably confusing the units for specific heat with the units for heat of combustion. Well, so to set this out, when you talk about the heat of the reaction, there's two common units. You might talk about the heat that's produced by a particular reaction, and then you would say that the units are joules or kilojoules. Or you might want to phrase the heat in terms of joules per mole or kilojoules per mole. These are the two common ways to phrase the energy of a reaction, or the heat of a reaction, or the enthalpy of a reaction. These two separate ways. So for example, so far here, we've expressed that this particular reaction of this particular mass is producing 19.34 kilojoules. Now let's also re-express this in terms of kilojoules per mole. How would you rewrite that in terms of kilojoules per mole?
How would I rewrite Q of the reaction in kilojoules per mole?
So here was our answer. We said here that when we burned 1 gram of hydrazine, it produced 19.34 kilojoules. How could we re-express that answer in terms of kilojoules per mole?
Just divide it by 1 mole.
So
take 19.34 and then multiply it, or I'm sorry, divide it by 1 mole.
Okay. Now, the problem with that is that would give you the right units, but then you would be writing this. That would give you the right units, but then you would be saying, so that would be 1 mole of what?
Oh, I see what you mean.
This is moles of what?
It could be anything.
But for this problem, it would be moles of what?
N2H4.
Yes, but we didn't actually burn 1 mole of N2H4, or we can't assume we're burning 1 mole, so we can't just stick the number 1 down here. How many moles did we actually burn?
0.03125.
That was a number that you hadn't had to use yet. So what do you get when you do that calculation?
$618.88. So 619 kilojoules per. Yeah, that'd be the heat evolved upon the combustion of. Well, that's not 1 mole, but I do get 619 kilojoules released.
Now, how would you interpret this number?
For every 0.03125 moles of N2H4, once that's combusted, it'll release 619 kilojoules per that mole of N2H4.
Okay, so there's a problem with that interpretation. So it sounded like to interpret this, you actually took this number and you combined it with this number down here. But those are in 2 different ratios, so it doesn't make sense to use them in a single interpretation. Actually, so what you just said is that if we combusted 0.03 moles, it would produce 618 kilojoules. But we know that's not true. How much energy do you actually release when you combust 0.03 moles?
Negative 19.34.
Yeah, we actually know from this problem that if you combust 0.03 moles, that releases 19 kilojoules. So it wouldn't make sense to say this is the amount of energy when you combust this. Try again. How would you interpret this number, the 618.88?
That would be, well, since it's 19 for every 0.03125 moles, then that means that 619 kilojoules are released per 1 mole of N2H4.
Okay, yeah. Isn't that how we always interpret fractional units? That's a technique that you were using quite a bit yesterday. So in order to, we've talked a bunch about how do you interpret fractional units. The way to interpret fractional units is to put a number in front of each of the units. So we need to put a number in front of the moles. But we need to put a number that's not going to change this numerical quantity. So what number can we put on the bottom here?
A 1.
That's the only number we could put down here without changing the whole numerical quantity. So then we can interpret that to mean if we combusted 1 mole of hydrazine, it would produce approximately 619 kilojoules of heat.
But how come we can assume that negative 19.34 is released per 0.03125 moles?
Because we know it. Because you figured that out. You figured that out. They said that in this problem they were combusting 1 gram, and we know that 1 gram, you figured that out, is 0.03125 moles. So that you know that in this, one thing that might help here is that when you're interpreting numbers, some numbers are actual and some are hypothetical. I don't remember if we've talked about that before, but some numbers are actual and some are hypothetical. For example, let's take a look, say, at this number. 32 grams hydrazine. Is that actual or hypothetical? That's hypothetical.
Actual.
That's actually hypothetical. Because do we actually have 32 grams of hydrazine in this problem?
No.
No. So this is hypothetical. This is hypothetical. This is how much hydrazine you would hypothetically have if you had 1 mole of hydrazine. What's the, how about this number? Is this number actual or hypothetical?
That's actual.
That's the actual mass that we actually had in this problem. This is just hypothetically how much we would have if we had 1 mole. How about this number? Is this number hypothetical or actual?
That's also hypothetical.
That's right. This is the number of moles you would have hypothetically if you had 32 grams. But we don't actually have 1 mole. How much moles do we actually have?
We have 0.03125 moles.
That's right. This is the actual number of moles. So I guess that's a subtle issue that people oftentimes don't understand in chemistry. Some of the numbers you're working with are hypothetical and some are actual. This number is the actual number of moles we have on the problem, and this is the actual mass that we have. And these were some hypothetical numbers. Usually you use hypothetical numbers to find conversion ratios. Usually the conversion ratios are based on hypothetical numbers. You use the hypothetical numbers and the conversion ratios to convert from one actual number to another actual number. So how about this number? Was this hypothetical or actual?
That was an actual number.
This is the actual number of joules that were produced in this case. And this number, so what we did here is we took, so when you're creating a ratio, you want to be consistent. When you're creating a ratio, it's good to put an actual number on top of an actual number. Or, for a ratio, you might have a hypothetical number on top of another hypothetical number. That would also be good. But you can't mix and match. Your ratio doesn't make sense if in one part of the fraction you're putting an actual number and in the other part of the fraction you're putting a hypothetical number. That would be bad. You're not supposed to do that. That's kind of what you tried to do at the beginning. When I asked you to figure this out in terms of kilojoules per mole, you started by just writing the number 1 mole on the bottom. And you were probably doing that because when we interpret, because we oftentimes do write a number 1 on the bottom, but that's when both numbers are hypothetical. Here, we actually knew that we actually were producing 19.34 kilojoules. Since we're actually producing 19.34 kilojoules, since this is an actual number, we have to put the actual number of moles on the bottom in order to be consistent. Then when you do that division, you got this new number, 618.88, which could also be interpreted as 618.88 over 1. So now, is this number, 618, is this actual or hypothetical?
That's actually hypothetical.
How do you know? Because we know we didn't produce 619 kilojoules in this reaction. We actually produced 19 kilojoules. This is the hypothetical heat that you would produce if you hypothetically combusted 1 mole. This is the actual heat you would produce when we actually, in this situation, when we actually combusted 0.03. I've been talking for a while. I kind of forgot exactly what your original question was, but maybe that makes it a little bit clearer what was wrong with your original approach and how to set up these ratios. I don't know, does that answer your question or not?
Yeah.
Okay. All right. I know this is a little bit of a subtle issue between actual and hypothetical, but this is worth going over because we keep working with these ratios over and over, and people have a hard time thinking about them here. All right. So, so what we did here is we used the two actual numbers to figure out hypothetically how much would be evolved upon the combustion of a mole. So notice that this first question here is kind of, well, yeah. All right, so here we got the actual amount of heat, and here we kind of figured out the hypothetical amount of heat that would hypothetically produced if we combusted 1 mole. Let's see, so where were we? So what do you think then, so how would you interpret this 618.88?
So for every 1 mole of N2H4 combusted, it'll release 618 kilojoules.
That's right. Maybe it would be a little bit more precise or concrete to say, if we hypothetically combusted 1 mole of hydrazine, then we would hypothetically produce 618.88 kilojoules. That makes it a little bit more concrete, I think. All right. So that's how we can go from the actual kilojoules to the kilojoules per mole. So what was the answer to the first question here?
Negative 19.34 kilojoules.
Good. I'm not sure quite, but this word evolved, maybe the word evolved already implies that the heat is being released. So maybe it would be redundant to say negative. Maybe it would be better to say 19.34, but I'm sure your instructor wouldn't be picky about that. So that doesn't matter. So that's a good answer. And what's the answer to the second question?
618 kilojoules per 1 mole.
Yeah, we know that there will be 618.88 kilojoules per mole. That was the way to answer the second question. At first, it sounded like you were focusing a little bit too much on the word combustion here. But remember, both of these questions are about combustion. The first question is asking the heat evolved when we combust 1 gram, and this is asking the heat evolved when we combust 1 mole. Okay, so you figured out how to get the Q reaction pretty easily. Then you had some trouble with this second question. So that would be a good thing to go back and review. Let me remind you, so notice this question is talking about a bomb calorimeter. Do you remember what a bomb calorimeter is? It looks kind of like this. I guess the bomb wouldn't really be floating in the water usually. So we'd have, here's like, this is like a cartoon of what it looks like. So here's the bomb. Remember that the bomb is just a sealed vessel, and the reaction takes place in here. And then heat can move out of the bomb So that's surrounded by water. And the whole thing here is sealed again with a constant volume. So notice that in these problems, they tend to give you not the specific heat, but the heat capacity of the whole apparatus. So notice we didn't have to worry specifically about the specific heat of the water or the bomb or the container. They just give you the heat capacity of the whole apparatus. And then you can use this equation with a capital C for that when you're working with the bomb calorimeter. Okay? Let me actually make one more comment about the previous problem here. So I just wanted to point out, now we've kind of gotten to the practical importance of calorimetry. How is calorimetry used in real life? Well, let me ask you this. So if you look at like the back of your textbook, there'll be a whole bunch of tables. There'll be what are called thermodynamic data, and they might have things like, it might not be in the back of the book, but somewhere in the book there'll be things like the heat of combustion of a whole bunch of substances. How do they figure out? That's how much heat is released when you combust various substances like octane or butane or methane or methanol or ethanol. How can the scientist figure out how much heat is released when you combust something? What would be a real-life way that a scientist can figure out those numbers in the textbook? How can a scientist figure out the heat of combustion of something?
Using bomb calorimetry.
Yeah, so I just want to make sure that it's clear that just doing the process we just did, because notice that all that the scientist has to be able to measure here, well, they need to already know the heat capacity. They need to already know the heat capacity of the calorimeter, which they could have previously measured using known amounts of heat. And then all they have to do is measure how much of the substance they're reacting, and they can easily measure the temperature change. So the point here is it's not easy to measure heat directly. It's not easy to measure heat directly, but we can measure temperature directly. We can measure temperature easily, and then this is the key equation. Since you can measure the heat directly, you can easily use this equation to figure out, since you can measure the temperature directly, you can easily figure out the heat that's coming from the reaction. So that's the main reason we're studying this, because this is an important practical technique in the lab. What do you think calorimeter means? Do you know what calor means? Calories mean heat, basically, and meter means measure. So it's called a calorimeter because it's a way of measuring heat. It doesn't measure the heat directly, it kind of measures the temperature directly, but then you can calculate the heat. So that's the practical importance of what we're talking about. That this is a way that the chemists can come up with all those heats of the reactions that they give in the textbook. All right, now let's try this problem.
A 0.5865 gram sample of lactic acid is burned in a calorimeter whose heat capacity is 4.812 kilojoules per degree Celsius. The temperature increases from 23.10 to 24.95. Calculate the heat of combustion of lactic acid per gram and per mole. Well, what they're asking for is the heat of combustion, which of the reaction, which is QRXN.
Good.
And we can predict that it's going to be negative because it hasn't evolved. So then what we can do is
let's talk about that prediction again for a second. So you were predicting Q reaction would be negative. What was your reasoning there again?
Because none of the heat evolved.
Okay. Now, I'm not quite sure what you meant by that. They didn't use the word evolved in the problem. But I think when you say that heat is evolved, that just means heat is released or produced by something. So I think that was the wrong way to think about this. What type of reaction is occurring here?
A combustion.
And is that exothermic or endothermic? Exothermic. So would the heat of the reaction be positive or negative?
Negative.
All right, so that's how we know the heat of the reaction is negative, because we know from outside knowledge that combustion reactions release heat. It's not because they didn't use the word evolved in the problem. I think evolved just means produced or released. But in the previous problem, they told us that heat was being released. But even if they don't tell us that, we know that anyway for a combustion reaction. Okay, so let's continue solving the problem.
So Q calorie is equal to C delta T, where that is equal to 4.8125 kilojoules per degree Celsius. Then you can multiply that by the temperature change, which is 1.85 degrees Celsius. So 4.812 times 1.85, that is equal to 8.9022 kilojoules for the Q calorie. Now we can take .5865 grams lactic acid, and then what we can do is we can turn it into moles. That's 36 plus 48 plus another 6 is equal to 90 grams per 1 mole. And that is equal to 0.0065 2 moles lactic acid. Now we can do then take the 8.9022 kilojoules and then divided by the 0.00652 moles lactic acid. And that gives us 1,365 kilojoules per 1 mole of lactic acid. And then we can take 8.9022 kilojoules and divide that by 0.5865 grams of lactic acid. And then that'll give us 15.2 moles, or sorry, 15.18 kilojoules per 1 gram lactic acid. And both of those are going to be negative Qs.
So what's your answer to the question?
Negative 1,365 and negative 15.2 kilojoules.
Now, our first answer should really, in this case, I think it should be negative 1365 kilojoules per mole, since
Yes.
that's what they were asking us for. And the second answer should be negative 15.2. kilojoules per gram. Okay. So let's see here. So what did you, so you have to be careful when you're doing this, you, for the temperature change, to do final minus initial. I think you did that correctly. So what was the Q for the calorimeter?
Q for the calorimeter was 8.9022 kilojoules.
Positive or negative?
Positive.
You can see it came out positive from the problem. But what we want is Q for the reaction. So what's Q for the reaction?
Negative 8.9022 kilojoules.
We probably should have written that down as a separate step, to be clear. And then this is the number that we should be using then to answer the question, this negative number, because we want to know the heat from the reaction. We don't really care directly about the calorimeter. So then this matches our prediction that this comes out to be negative. Okay, and then, so notice you want to pay close attention to the units that they're expecting for the answer. So here's a third way you can describe the heat of the reaction. You can describe the actual heat that was produced in the actual reaction, or you can hypothetically describe the amount of heat that would hypothetically produced if you reacted 1 mole. Or you can hypothetically describe the amount of heat that would be reacted if you reacted 1 gram. Those are 3 different ways to describe the heat of a reaction. So you have to pay close attention to how the question is worded to see which one you want. Okay, good. That was a good process. Let's try this problem.
moles is equal to moles over liters. So 2 mole is equal to x moles over 0.030 liters. We can cross multiply and we get moles is equal to 2 times 0.03, and that's 0.06 moles NaCl.
Okay. It would be good to always start by identifying the question. Here, it's a good idea to maybe identify the right units for our answer. So what would be the units for our answer?
Moles
of NaCl. Now, the way you solved this problem was by setting up a proportion. And I think you did that correctly. So that was a good method. You can use a proportion to solve this. But as chemistry problems get harder, the proportion method turns out not to be a good method, and instead it's better to use unit conversion. If we were going to do this as a unit conversion, we would say that our target units are moles of NaCl. How would you do this problem as a straightforward unit conversion then, not as a proportion with an equation?
Well, we can write 2 molar as, well, we can say, we can take 30 milliliters and then multiply it by 1 liter and divide it by 1,000 milliliters to get liters. That way the milliliters will cancel out.
Good.
And then we'll be left with liters. Then what we can do is we can write the molality as moles x, no, I guess you can say x moles over liters over 1 liter. That way the liters will cancel out.
So we need to put in another conversion ratio here. It wasn't clear to me. What are you writing on the top and the bottom of this conversion ratio?
X moles and then 1
now,
liter.
When we're doing a unit conversion, we don't usually use variables. That would be the proportion approach. So the point here is, so what does this capital M stand for?
Molarity.
Molarity. I think a second ago you were saying molality, but you're right. This stands for molarity. How can we rewrite that then? 2 molar NaCl. How could you rewrite that in other units? What does that really mean?
That means 2 moles per 1 liter.
2 moles of NaCl per liter. And it helps to put a number on the bottom. Well, the only number we could put on the bottom without changing the numerical value of the molarity is the number 1. So the point is that molarity is really a fraction. Molarity is really a fraction, but what we've seen is that whenever you have fractional units, you can use that as a conversion ratio. Whenever you have fractional units, you can use that as a conversion ratio. So how can we use this to get a conversion ratio here?
So then we can put 2 moles over 1 liter on the top.
What would
2 moles of NaCl.
Yeah, and what would you put on the bottom?
1 liter.
Right. And then what?
Then you can just take 30 divided by 1,000, cancel out the liters, and then multiply that number by 2, and you'll get the moles of NaCl.
So do that calculation. What do you get?
.06.
Good. That's the same answer you got before. So when you did use a proportion. So there's nothing wrong about using a proportion, but as I was saying, as the problems get harder and harder, proportion method becomes unwieldy. It's better to get into this habit of using the unit conversion approach. When you're doing a unit conversion, if you're trying to find something that's not a fraction, it's usually best to start with the number that's not a fraction. So notice here, we didn't start with the 2 molar, we started with the 30 milliliters, because that's not a fraction. We start with one number that's not a fraction, we multiply it by a bunch of fractions to find a new number that's not a fraction. Also with practice, I think it's good to do this all in one fell swoop, rather than breaking it up into pieces. Okay, so what we've seen here is that molarity can be used as a conversion ratio. Anytime you have fractional units, that can be used as a conversion ratio. That's a good thing to have in your notes. Anytime you have a concept that has fractional units, it can be used as a conversion ratio. Notice here that we can again see the difference between actual and hypothetical numbers. For example, is this number actual or hypothetical?
That's actual.
You're saying that in this problem we actually had 1 liter?
Oh, no. No, we actually had 30 milliliters.
Yes. This is hypothetical. This is the volume if you hypothetically had 2 moles. If we had 2 moles of NaCl, that would hypothetically be 1 liter, even though we actually had 30 milliliters. So how about, say, this number? Is this number actual or hypothetical?
That is hypothetical.
Because how many moles do we actually have?
0.06.
Yeah. Usually the numbers on the top and the bottom of your conversion ratio will be hypothetical. And you multiply those by one actual number to find another actual number. That's the usual approach. You start with an actual number, and then you construct that. Then the numbers on the top and the bottom of the conversion ratio are hypothetical, and by doing the multiplication, you get a actual number. For that matter, is this number actual or hypothetical? Was this actual or hypothetical, this 1,000?
That is, hypothetical. Well, actually, no. That is, the 1,000 is actual.
Well, do we actually have 1,000 milliliters in this problem?
No.
So it's not actual. It's hypothetical. This is the amount of milliliters you would hypothetically have if you had 1 liter of solution. Again, both of these numbers, these are in conversion ratio, they're both hypothetical. Maybe the reason you said actual is because you were thinking, well, gee, there actually are 1,000 milliliters in 1 liter. That's true, but we don't actually have 1,000 milliliters in this problem. That's why I would call it hypothetical. So this is saying if we hypothetically had 1 liter, that would consist of 1,000 milliliters. But these are both hypothetical numbers because they don't represent the actual volumes in this problem. This is the actual volume in this problem. So again, conversion ratios generally consist of hypothetical numbers on the top or the bottom, and you multiply those by one actual number to get another actual number. All right, so how would you do this problem?
Now we take 40 milliliters. And then we can multiply that by 1 liter over 1,000 milliliters. And then we can take 0.8 moles over 1 liter. All the units cancel. And then we get 0.032 moles AgCl.
What was your answer again?
.032 moles AgCl.
Okay, that's right. Let's try this.
And 50 milliliters of 1 molar HCl and 50 milliliters of 1 molar NaOH are mixed in a coffee cup calorimeter. The temperature of the resultant solution increases from 21 degrees C to 27.5 degrees Celsius, assuming that the calorimeter absorbs only a negligible amount of heat, that the total volume of solution is 100 milliliters, and specific heat is 4.18 joules per gram degree Celsius. Calculate the enthalpy change for the reaction. Well, everything's a 1 to 1 to 1 to 1 ratio. Then what we can figure out are the moles of each. So we have 50 milliliters HCl times 1 liter over 1,000 milliliters times 1 mole over 1 liter. Then we get 0.05 moles HCl. And then we'll probably have the same amount of moles of NaOH as well. So we have also 0.05 moles NaOH.
That's good. Let's also write down a symbol for what the question's asking us.
It's asking us for the enthalpy change for the reaction, so that would be Q of the reaction.
Good. That's good. And what would you predict here?
I would assume that well, since it's not a combustion, but since there's an increase, it's going to be negative because there's an increase there's an increase in temperature. Yeah, I assume it's negative because there's an increase in temperature.
Who's negative?
Q of the reaction.
Good. So is the calorimeter absorbing or releasing heat?
It is absorbing it.
Because its temperature is going up. So is the reaction absorbing or releasing heat?
The reaction is releasing it.
Good. So that was good that you worked that out. It's good that you noticed this is not a combustion anymore. You can use calorimetry for any reaction, or most any reaction, not just combustion. So we couldn't just assume that this would be exothermic, but you can see it is from what's happening to the temperature. So it's always good to start with those steps. Okay, now what?
Well, now you can figure out Q for the calorimeter, which is equal to capital C delta T, where Q for the calorimeter is equal to 4.18. Oops, not 4.18. Well, we can't figure out Q for the calorie because we don't have the
I think I left out some information.
Heat, I'm sorry, not the specific heat, but the heat capacity of the calorimeter. However,
yeah, excuse me,
we do have a change in
some
temperature.
Information here. Sorry, I left out some information. Stop. I left out some information. So let's see here. We've got total volume. Rats, I left something out. Okay, I should have added this extra piece of information. So you need to add that to the problem. And now we should try to solve the problem.
Well, since we can't figure out Q calorie, we can figure out, we are given the specific heat, a change in temperature, and a volume, so we can use specific heat of the reaction. Q is equal to m lowercase c delta t. So Q is equal to 100 grams times 4.18 times the change in temperature, which is 6.5. And that is equal to 4.18 times 6.5 times 100 is equal to 2,717 joules. So we know the heat capacity of the enthalpy change of the reaction.
What number did you get here again? For the heat of the calorimeter?
2,717 joules.
Okay, good. Let me ask you, where did you get this 100 grams from?
I did the unit conversion where we have 100 milliliters times 1 gram per 1 milliliter, so the milliliters cancel out and you're left with grams.
Good. That's why I had to give you that extra piece of information. I had to tell you that the density was 1 gram per milliliter. So yeah, the solution's 100 milliliters, so it's also 100 grams. So I think we saw last time that we can use density as a conversion ratio. So we're seeing that anytime there's fractional units, you can use that as a conversion ratio. Okay, that's good.
And that'll be our, and since that's, so then our Q for the reaction is equal to a negative 2,717 joules.
Is that your answer?
Yes.
Okay. All right. So that was actually a good process here. So let's see. So you adapted correctly here. You started by using this equation. What does capital C stand for? What's the capital C stand for?
That is heat capacity.
That's right. What does lowercase c stand for?
Specific heat.
Yeah. All the problems we've done so far, we were using heat capacity. So it's good that you adapted and you saw this problem was about specific heat. What's the clue that this problem is giving you the specific heat and not the heat capacity?
Because it says the specific heat.
So first of all, they use those words. It
tells us the specific heat.
They use the words. What if, even if they didn't give you those words, you should be able to tell just from looking at this that it's a specific heat and not a heat capacity? How can you tell? How can you tell just from looking at this that it's a specific heat and not a heat capacity?
Because they give us, well, apart from the specific heat, they give us a change in temperature, and they also somewhat, we can figure out a weight for based on the density and the volume.
Now, that's not really what I was getting at for how we can look at this and see that it's a specific heat and not a heat capacity. What I meant was, what are the correct units for specific heat?
Joules per gram degrees Celsius.
And what are the units for heat capacity?
Joules per degree Celsius.
So that's what I meant. That's how we could look at this and see that it was a specific heat and not a heat capacity, even if they didn't use that term, from looking at the units. So you had to switch equations. That was good, that you switched equations there. Now, remember that we know that the problems can be a little ambiguous because sometimes when they're asking for the energy change, they mean joules, and sometimes they mean joules per mole. In this case, they were a little ambiguous, but they said they wanted the enthalpy change for this reaction. and then they wrote the reaction, when they actually write the reaction out, that they're implying that they want the general enthalpy change, not the enthalpy change for this particular set of reagents. So when they write it like this, they're implying that they really want the answer to be in joules per mole. So we're actually not quite done with this problem. Since they were asking for the enthalpy change for this general balanced equation, that's really a way of implying that they want the answer in joules per mole. So let's keep working. How could we give an answer in joules per mole? And so let me give you a hint here. So what that means here is that you would want to figure out the answer, say, in joules per mole of one of the starting materials. That's the convention. Joules per mole of one of the starting materials. So let's figure it out in terms of joules per mole of HCl.
So since we have half a mole of HCl, we can take our 2,717 divided by half a mole, and then that'll give us negative 5,434 joules per 1 mole of HCl. And since that would also be the same because we have their 1-to-1 molar ratio, so it'd also be negative 5,443 per 1 mole of NaOH.
How many moles of HCl do we have?
Half.
Let's see. Where did you get that from?
I'm sorry, not half. It's 0.05. So whoops, that was negative 54,340 joules per 1 mole of HCl and NaOH.
So I think this would be the answer that they're going for. Maybe we should put that into kilojoules since this is a big number.
It would be negative 54.34 kilojoules per 1 mole of HCl or NaOH.
That's right. I think you're generally going to be given problems where you're going to start with the same number of moles of both starting materials, so you can choose either one or the other. Notice that the convention is you don't add the moles of the two together. You don't add 0.05 plus 0.05. You just choose one of the starting materials. When you're expressing the joules per mole, it's just joules per mole of one of the starting materials. So I think this is the answer they'd be going for here. So you kind of have to read between the lines to see how they want you to express the answer. Now, this is the first problem that we've done that was about a coffee cup calorimeter. Do you have a lab in your class? Lab work?
It's separate from the lecture.
But are you taking lab?
No.
Oh, okay. All right. Well, if you were taking lab, then you might actually do this experiment. So we've seen that the bomb calorimeter looks like this. What's a coffee cup calorimeter? Well, the coffee cup calorimeter is just where you use a styrofoam coffee cup filled with water. Actually, I guess you usually use 2 coffee cups for extra insulation nested around each other. But anyway, you just have a coffee cup and you do the reaction in that coffee cup and you measure the temperature that's occurring there. The basic idea is pretty similar to the one with the bomb calorimeter. The coffee cup provides insulation, so you're not losing or absorbing heat to the outside environment, but it's not completely sealed, so it's in contact with the atmosphere. So a coffee cup calorimeter maintains constant pressure. Since there's contact with the atmosphere, you're at atmospheric pressure, whereas the bomb calorimeter maintains constant volume because it's a sealed fixed volume. For the most part in this class, I don't think it's going to make much difference for solving problems. You're going to solve the problems pretty much the same either way. This problem asked you for the enthalpy change. That's a concept that we haven't talked about before. the symbol for enthalpy change is delta H. And that pretty much is just the heat. It's pretty much the same thing as Q, but it's the heat that is released at constant pressure, or it's the heat exchange at constant pressure. Enthalpy is defined as heat exchange at constant pressure. So it kind of means the same thing as Q, except that Q is just heat exchange in general, and enthalpy change is heat exchange at constant pressure. So notice that a coffee cup calorimeter is a great way to figure out delta H because it maintains constant pressure. The coffee cup calorimeter, the reagents are in contact with the atmosphere, so they're at atmospheric pressure. So the calorimeter is a good way to find delta H. Technically speaking, you don't find delta H directly from the bomb calorimeter because the bomb calorimeter doesn't maintain constant pressure because the reagents are not in contact with the atmosphere in the bomb calorimeter because it's sealed from the environment. So the symbol that you would usually use for what you're finding directly from a bomb calorimeter is just delta E, which I guess is the same thing as Q for our purposes. So the Q that we're figuring out would really tell you the delta E, the energy exchange for the reaction, but not necessarily, really the energy change at constant pressure. That's usually not gone into in too much detail in an introductory course, so I guess we don't have to talk about that much more. But I just wanted to warn you, if you're doing a coffee cup calorimeter problem, they might ask you for the enthalpy change. Whereas if you're doing a bomb calorimeter problem, they probably won't ask you for the enthalpy change, they'll ask you for the delta E, or the heat, or the energy exchange. But you would solve them both the same way. The way to solve both of these is just to find Q reaction. Either way, you solve it by finding Q reaction, which you do by finding Q for the calorimeter. So basically, you would just solve it. So you can see from the problem we just did that the way of solving is pretty much the same for the coffee cup calorimeter and for enthalpy change as it would have been for a bomb calorimeter. We didn't change things much. Now, another complication here is notice that the coffee cup calorimeter kind of has two components. It's got water, or it's got the solution, and it's got the coffee cups. It's the water solution plus coffee cups. By the way, you can see you wouldn't do a combustion reaction in a coffee cup calorimeter. You're not going to burn something inside of a coffee cup. These are just reactions you can do in solution. For combustion, you would use the bomb calorimeter. In the problem we just did, notice how they specifically said that the calorimeter absorbs a negligible amount of heat. What do they mean by the calorimeter? Well, they basically mean the coffee cups plus the thermometer. The calorimeter is just the solid apparatus, the coffee cups and the stopper at the top. You might have a stirrer and a thermometer. So the calorimeter is kind of the apparatus, the coffee cup and the other solid apparatus. They said the calorimeter was absorbing a negligible quantity of heat. So who was absorbing the heat in this problem?
The calorimeter.
Well, remember they said that the calorimeter itself was absorbing a negligible quantity of heat. By that they meant the solid parts. So which part is absorbing the heat? It was the solution that was absorbing the heat, right? They said that the solution is 100 milliliters and its specific heat is 4.18. That means that it was the watery solution that was absorbing the heat. You don't expect the styrofoam cup to change temperature very much. That was a way of simplifying this problem. But what if you had a situation where both the solid portions and the solution was absorbing heat? Then they might do something like they might say, instead of saying that the calorimeter absorbs a negligible quantity of heat, they could say, assuming that the calorimeter, so I'm going to change the problem to make it harder. Assume that the calorimeter has a heat capacity of 400 joules per degree Celsius. Now, when they phrase it that way, they mean the solid portions of the calorimeter, like the styrofoam cup and the stir and the thermometer and the stopper at the top. And then they say the solution, the liquid solution, has this specific heat. So now, how would you find the Q for the whole calorimeter? Well, now it's going to be one portion from the heat that's absorbed by the solution, and another term for the heat that comes from the solid portions. Now we have two different components that are absorbing the heat. We know to use specific heat for the solution, because that's the number they gave us, as specific heat. And we know to use heat capacity, capital C, for the solid portions, because they gave us a heat capacity. So now, what would I plug in for capital C?
What was your question? I'm sorry.
Do you see why now we would modify the equation to look like this? Now the heat that's absorbed by the whole calorimeter has two portions. The heat that's absorbed by the solution and the heat that's absorbed by the solid portions. Well, you've already plugged in the numbers for the solution. What numbers would we plug in here for this term now? What would we plug in for capital C?
That would be 400 joules per degree Celsius times the same 6.5 temperature change.
Then what? What would we do next?
Then we would add the two.
Okay, so let's do that and see what you get.
So we add 2,717 plus 2,600. Get 5,315 as Q for the whole calorimeter.
The other number was 2,600?
No, I got 5,317 as a total.
Yeah, so the number, this term was 2,600, right?
Yeah.
So then what would it be in joules per mole?
So divide this by 0.05. It needs to be 106,340 joules per 1 mole.
So in kilojoules per mole?
I'm sorry?
What would the answer be in kilojoules per mole?
It'd be 106.34 kilojoules per mole.
Okay. So this is a harder type of problem. I'm not sure whether you would see this on the test or not. So the problem gets harder. In the original problem, they just told us to focus on the heat that was absorbed by the solution and to ignore the portions that were absorbed by the solid parts of the calorimeter. But it's possible that they might also want you to take into account, it's possible that the calorimeter might also be absorbing a significant amount of heat. How can you tell which one it is? Well, you just use whatever specific heats and heat capacities they give you. Whatever specific heats and heat capacities they give you, those are the things that they want you to use to solve the problem. So here's a more difficult type of problem that they might give you. Like I said, don't assume the problem is like that, though. But if they give you more than one specific heat or more than one heat capacity, you need to figure out the heat for each part separately and then add them up, like we did here. If they only give you one heat capacity or one specific heat, that's a strong clue that that's the only thing you have to consider in the problem. Let's try this problem.
I don't quite follow your reaction.
AgNO3 aqueous plus HCl aqueous forms AgCl solid plus NaCl aqueous. You mean you can't read my writing, or something doesn't make sense?
Well, you say that we have 1 molar AgNO3 and HCl. I'm not sure where the sodium is coming from.
Good point. That's a good point. Let's try it this way instead. Oh, it's still not working, is it? What did I want here? Why am I getting confused? AgCl. Let me think for a second. How can I fix this? Okay, I think now the problem makes sense. Let's try this.
When 50 milliliters of 0.1 molar AgNO3 and 50 milliliters of 0.1 NaCl are mixed in a constant pressure calorimeter, the temperature of the mixture increases from 22.30 to 23.11. The temperature increases is caused by the reaction. Calculate delta H for this reaction, assuming that the combined solution has a mass of 100 grams and a specific heat. Okay, well, we can take 50 milliliters.
Let's start by writing the symbol for what the question's asking.
It was asking for delta H. And we can predict
write that as
it's going to be
delta H.
negative because it's a reaction, and we can just assume that they're all exothermic.
Okay, that answer I think was incorrect. You can't just assume that all reactions are exothermic. Some are exothermic and some are endothermic. So try again to get a prediction.
Well, since the temperature increased, we know that heat is going to be released from the reaction.
So what's your prediction?
That delta H is going to be negative.
Yeah. So we don't assume the reaction is exothermic, but we can see that it is from the change in the temperature. They must be releasing heat so that the calorimeter's temperature can go up. Okay, now you can continue. Good.
So we can take 50 milliliters and times it by 1 liter over 1,000 milliliters and times that by 0.1 moles over 1 liter, and we get 0.005 moles. And they're both at a 1-to-1 ratio, so you have moles, 0.005 moles AgNO3 and NaCl. Then we can figure out
how many moles did you say you had?
0.005.
Let's see, you had 0.1 moles of AgNO3 per liter, so 50. Like this?
Yes.
Okay, good. Good.
And then now you can figure out, since it's at constant pressure, we don't have to take into account the calorimeter. So Q, the reaction, is equal to mc delta T, where Q is equal to 100 grams times 4.18 times change in temperature, which is 0.81. So 100 times 4.18 times 0.81 is equal to 338 kilojoules. Now we can take 338 kilojoules and we can divide it by 0.005 moles. I'm sorry, that's in joules, not kilojoules. So joules divided by moles. We get 67,716 joules per 1 mole. And this is going to be a negative number.
What was that last answer again?
Negative 67,716.
Okay, good.
And then we can divide it by 1,000 joules to get kilojoules, so it'll be negative 67 kilojoules per 1 mole AgNO3, and 1 mole, and the same number per 1 mole of NaCl.
Good. What would you round that off to?
Negative 68.
Negative 68. Okay. So let's see. Now, so here you were using MC delta T. Now, what you said was that gives you the Q for the reaction. That's actually incorrect because whose temperature is changing here?
The calorimeter.
Yeah, or the solution in the calorimeter. So this actually gives us the Q for the calorimeter, or the solution in the calorimeter. So we shouldn't say this is Q reaction. This is the Q for the calorimeter or the solution in the calorimeter. So that came out to be positive. And then it wouldn't hurt to write as a separate step, Q for the reaction is the negative of that. We discussed that last time. Any heat that's absorbed by the calorimeter solution must have been released by the reaction. So it would be good to write that as a separate step. That's the reason then when we're doing the heat of the reaction, we put in a negative number. Notice that because this was a constant pressure calorimeter, they can ask you for enthalpy change, because this is occurring at constant pressure. But even though they said delta H, really we just solved this as before by finding Q reaction. We find Q reaction to find the delta H. It doesn't really change anything about how we solve the problem. And remember that we only put in the moles of one of the starting materials. That's the convention. There was one thing that you said that I think was incorrect. I think you said that we don't have to consider the solid portions here because this is occurring at constant pressure. You said something like that. That's not the correct way to think about it. How do we know that in this case we should only pay attention to the heat that's absorbed by the solution and not the heat that's absorbed by the solid parts of the calorimeter? The way we know is that they only gave us a specific heat for the solution. They didn't give us any heat capacity for the solid parts of the calorimeter, so it's implied that the heat absorbed by the solid parts will be negligible. So that's how we know to ignore the other the solid parts, because they didn't give us the information we would need if they were important. It's not really specifically because it's constant pressure. Okay, so anyway, though, that was a good process, and I think you got the right answer. At first, I think you had the wrong units here, but then you realized that this should be in joules. How do you know that this number came out in joules?
Because the specific heat is given in joules.
That's right. So it's really important in all these problems to pay close attention to all the units. Now let's try in this problem?
.50-gram sample of NH4 NO3 is added to 35 grams of water in a coffee cup constant pressure calorimeter and stirred until it dissolves. The temperature of the solution drops from 22.7 to 21. What is the heat of solution of NH4 NO3 expressed in kilojoules per mole? Okay. So we have a 0. We have half a gram of NH4NO3.
Let's start by writing down a symbol for what the question's going to ask us.
Oh, they're looking for the heat of solution, which is Q, which is expressed in kilojoules per mole.
Good. Are they asking for Q reaction or Q of the calorimeter?
Q of the reaction.
Good. That's what they mean by heat of solution. They mean the heat of the solution reaction. Good.
Then the temperature drops from 22 to 21, so it most likely is going to be a positive Q since it's absorbing heat.
Who's it?
Q of the reaction.
Yeah, the reaction is absorbing heat. Absorbing the heat from who? From the solution. That's why the solution's temperature is dropping. Good. That was a good prediction. Okay, so then we can continue.
Now we have, let's see, 28. Nitrogen is 14 times 2 is 28. 48 plus 28 plus 5 is equal to 81 grams per 1 mole. So 0.5 divided by 81 is equal to 0.0062 moles NH4NO3. Now we have 35 grams of water.
What did you get as the molar mass?
81.
Try that calculation again.
Oh, 80.
Good.
I get 0.00625 moles, and then we have 35 grams of water. We can divide that by 18 grams of water per 1 mole. So 35 divided by 18. We get 1.94 moles of water. The temperature of the solution drops. So final minus initial, what is the heat of solution expressed in kilojoules per mole? And it's stirred until it dissolves. We have a delta T. We have we have two masses, but we're not given a specific heat.
That's a good point. We haven't quite talked about this before. You need the specific heat of what?
Water.
Okay, good.
So we know that C, lowercase c, is equal to 4.184 joules per gram per degree Celsius. And we have a mass, so you can say Q for the solution is equal to mc delta T where M is 35 grams times 4.184 times change in temperature, which is 21.6 minus 22.7. That's negative 1.1. So now we have 35 times 4.184 times negative 1.1, and we get negative 161 joules. Now we can divide this by 1,000 to get kilojoules, and that is equal to 0.161 kilojoules negative. Now, since that's the heat of the solution in kilojoules, now you have to express it per mole of NH4, so we can take this number 0.161 kilojoules and divide it by 0.00625 moles NH4NO3. And that is equal to negative 25 or negative 26 kilojoules per 1 mole NH4NO3, but since the temperature of the solution dropped from 22 to 21, that means it was releasing it. So that means that our prediction, or my prediction where it was positive, was wrong, and that it should be negative. So my final answer is negative 26 kilojoules per 1 mole NH4NO3.
Okay, now let's talk about that a little bit. Is the calorimeter here, is the calorimeter's temperature going up or down?
I'm sorry?
Is the calorimeter's temperature going up or down? Is the temperature of the calorimeter going up or down? Hi, are you still there?
Yeah.
Okay.
It's going up.
Why did you say that?
Well, oh wait, it's a coffee cup, so it also says that the temperature of the solution drops from 22 to 21, so I was thinking that would be like the reaction, the reaction solution itself.
Right. So is the solution's temperature going up or down?
It's going down.
So is the solution absorbing heat or losing heat?
It's losing heat.
So is the reaction absorbing or releasing heat?
It's releasing it.
I guess we're getting confused there. We have a reaction that's affecting the solution.
Okay, I see what you mean now. Then the reaction's actually gaining it.
Heat must be moving this way in order to cause the temperature of the solution to go down.
Yeah.
So would Q of the reaction be positive or negative?
So the reaction would actually be positive.
Which is what you predicted at the beginning. Now what happened here is that your math didn't match your prediction. Your math didn't match your prediction. So that means either your prediction was wrong or your math was wrong, and you just assumed that the math was right and that the prediction was wrong. But we can't assume that. One of the main reasons that we make a prediction is so that we can check our math. We should have more confidence in our prediction than in our math, because the prediction is more based on common sense. So when you saw that your math came up with a negative answer, what we should have said is we must have made a mistake in the math, not that we made a mistake in the prediction. We can be very confident that this is a correct prediction. because we know that the temperature of the water is going down, so it must be losing heat. So the reaction must be absorbing heat, taking heat out of the solution. So let's see where we went wrong here. Let's see. So this gives us here, so the problem here is that there's a little bit of ambiguity. When they say the heat of the solution, what they mean is the heat of the solution reaction. The question is asking us for the heat of the solution reaction. But when you wrote down the heat of the solution here, what you really meant was the heat of the water. The heat that the water itself was gaining or losing. The heat that the water itself is gaining or losing. So we got here that this came out negative because you did final minus initial. We know the water is losing heat. That was correct. So the Q of the water is negative 161 joules. So what's going to be the Q of this reaction?
Could you say that again?
What's the Q for the reaction? We know that the heat for the water is negative 161 joules, so what's the Q for the reaction?
So then Q for the reaction would be the positive 161.
So then what's the answer to the question?
Positive 26 kilojoules.
And does that match our prediction?
Yeah.
Yeah. Why did you get confused? Because we used the word solution to mean two different things. When the question asks for the heat of the solution, they don't actually mean the heat transfer to the solution. It's really pretty confusing. They mean the heat of the solution reaction. When they say heat of solution, they mean Q reaction, which is what you had identified at the beginning. But when you were writing Q solution here, you didn't mean the Q for the solution reaction. You meant the Q for the actual material water in the solution. It's really kind of confusing. We're using the word solution to mean two different things. That's the whole point, though, of predicting. You want to make sure your answer matches common sense. Common sense tells us that this reaction has a positive Q, so that we need to, if our math doesn't say that, it's better to go with the common sense than to get sidetracked by the math. This problem didn't give you the specific heat or the heat capacity. What should you do if they don't give you the specific heat or the heat capacity? Well, we know that the solution here mainly consists of water. So it makes sense to say that the specific heat here is the specific heat of water, even though they didn't specifically tell us that. What about the ammonium nitrate? Why are we ignoring the ammonium nitrate? Well, I guess we can ignore that because there's much, much less of that. Notice that there's way more water than ammonium nitrate. So we're just ignoring the ammonium nitrate and just hoping that most of the heat is going to be absorbed by the water and not by the solute. If you look at the questions that we did previously, think about this problem we did previously with the coffee cup calorimeter. We used this specific heat, but this is the specific heat of water, right? So basically in this problem, again, we were assuming that the water was the only significant thing absorbing heat and that the solutes were insignificant, even though we didn't say so explicitly. And I think we did that on the previous problem too. Here in the previous problem, we had a specific heat of 4.18. So again, we just assumed, that seems to be assuming that the water is the only significant thing that's absorbing the heat. And the solutes are insignificant. That's a pretty fair assumption because usually there's way, way more of the water than there is of the solutes. So in this case, the best thing we could do was just assume that the heat's absorbed mainly by the water to work that out. Okay. It's good that you paid close attention to the units here to make sure that your answer was in kilojoules per mole of the ammonium nitrate. Here, it makes a big difference whether we're using the ammonium nitrate or the water. Let's try this problem.
Zero 0.5056 grams of liquid cyclohexane undergo complete combustion of bound calorimeter. The calorimeter assembly has a heat capacity and contains exactly 1,000 grams of water, but the final, if the initial temperature was that, the heat combustion, okay. Well, they're looking for the final temperature, so we want TF. And since it's a combustion, we can assume that the final temperature will be greater than the initial.
So let's be more specific. What specifically are you predicting about the final temperature?
It's going to be greater than the initial.
Which was what?
24.98 degrees C.
Good. So we want to predict that. Good.
So now we can do Q is equal to MC delta T, where Q is equal to the 0.5060 grams times. Oh no, actually, no, it wouldn't be that because we don't have the specific heat. But we do have 1,000 grams of water. And since we know that the heat of combustion cyclohexanol is negative 3727 kilojoules per mole, that would be Q, so negative 3727 is equal to MC delta T, where 1,000 times 4.184 times the change in temperature, which would be TF minus 24.98, plus capital C delta T, where the capital C is the heat capacity of the calorimeter, and that is equal to 827 times the same change in temperature, TF minus 24.98. So now you can distribute and multiply.
Okay. Let me give you some help with this problem. So let's see here. First of all, it sounds like you're feeling that you have to separate this into two parts, one part for the water and one part for the solid portions. It sounded like you were separating this into two separate regions. Now, that's something that actually you might not actually see on your test. I went over that just in case. You may see that or you might not. How can you tell? Usually when you're going to have to treat the liquid and the solid portion separately, they're going to give you two different constants. They'll give you a specific heat for the solution and a heat capacity for the solid portions. So you shouldn't do that thing we were talking about of treating the two parts separately unless there's a strong clue in the problem that you have to. Remember that the previous problem where you had to do that, the clue that you had to do that was that I was specifically telling you both the specific heat of the solution and the heat capacity of the solid portions. Unless you're given both of those numbers, you're probably not supposed to do that on the question. Also, whose heat capacity? So what number were you going to plug in for capital C? What number would you plug in for capital C?
827.
That's right. Whose heat capacity is that?
The calorimeter.
Now, they gave you a clue here. Did they mean just the solid portions of the calorimeter or the entire calorimeter?
The entire calorimeter.
What's the clue word that tells you that?
Assembly.
That's right. So that's the other clue here. They said the calorimeter assembly has a heat capacity. By saying assembly, they mean the whole thing. By the way, remember, this is not the coffee cup calorimeter anymore. This is the bomb calorimeter. So in this case, we have the bomb and which is a sealed vessel inside of water, inside of another container. So it's a whole complicated apparatus. So by saying this, they mean that the whole assembly together has that heat capacity. So in this case, so there's two clues here that we should only have one term when we're figuring out heat. The first clue is they said assembly. So that means that this number refers to the entire apparatus. And the other clue is if they really wanted you to do MC delta T, just as a practical matter in your class, they would almost always give you that specific heat. They wouldn't expect you to come up with it on your own, even though you can, because you know it's 4.184. So you don't want to do this two-term approach unless there's a strong clue in the problem that you have to. You might not actually see that on your test. So let's go back to here. What should we plug in for capital C?
827.
And for delta T?
TF minus 24.98.
Good. And what we're finding here is Q for the calorimeter assembly. Now, one moment. And again, because they said assembly, we know that includes both the solid portions and the cyclohexanol and the water, everything together, at least approximately. What number did you plug in for Q on the left-hand side here for Q calorimeter?
Negative 3,727
Okay. What are the units on that?
joules. Or, sorry, kilojoules per mole.
What are the correct units? What units do we want this Q to be in?
Joules.
Okay, so we have a difficulty. Remember, we have to pay close attention to the units. It looks like you're plugging in a number that's not going to match with the other units in the formula.
Should actually be negative 3,727,000 joules is equal to.
Okay. Now, so so what are the units? So the number you're plugging in now here is what?
Negative 3,727,000.
And what units?
Joules.
Now, what number did you originally have? You had negative 3,727, correct?
Yeah.
What units did that have?
Kilojoules?
That's actually not correct. What units was this number in?
Oh, kilojoules per mole.
Yes.
So this would actually be joules per mole.
Good point. So, whoops. So, after you do this conversion, what units will you have?
Joules per mole.
That's right. What units is Q supposed to be in this equation?
It should just be in joules.
That's right. So we're not ready to plug this number into the equation yet. We're not ready to plug the number into the equation yet because it's not in the right units. We need to do more work on this before we can plug it in.
So then we have to get rid of the moles so we can convert the grams of cyclohexanol to moles and then multiply it by that to get the amount of heat released per that amount of moles. So then 0.5060 grams cyclohexanol. And that's 100 grams.
Good. So they didn't give us the formula for cyclohexanol in this problem. Did you go back to problem 1 for that?
So now we have 0.00506 moles. So now multiply the 3,727,000 by 0.00506 moles. And then that would give us 18,858 joules.
All right,
Negative 18,858 joules.
Let me get caught up with you here. So what's the next conversion ratio you wrote here?
So I divided it by I multiplied it by 0.00506 moles.
Moles of the cyclohexanol. How did you know that this moles down here referred to cyclohexanol?
Because it gave us the heat of combustion of cyclohexanol.
That's right. They specifically said this was the heat of combustion of cyclohexanol. So it makes sense that this is moles of cyclohexanol. So what did you get as this answer?
I got negative 18,858 joules.
Whoops. Let me check that. Negative 18,858 joules. Okay, good. That's right. Now what?
Now you can set up the equation negative 18,858 joules is equal to 827 times TF minus 24.98. You distribute the 827 and then you get negative 18,858.62
I guess I'm sorry.
827 TF minus 24.98 times 827 is equal
to... Sorry,
to...
I got to interrupt you again. 1 second. So let's see. What would be a good symbol for this number here? This number is equal to what?
827.
No, I'm sorry. This number here, what's a symbol for this number? What did we calculate here?
That's Q.
Q for what?
The solution.
Now, is this Q for the calorimeter or Q for the reaction?
Oh, it's actually Q for the calorimeter.
Oh, careful. I guess this is a confusing part of these problems. This number here, negative 3727, was that the heat of the reaction or the heat for the calorimeter?
That was the heat for the reaction.
And we were just converting it into something else. So this should also be the heat of the reaction. Maybe we should have made a prediction ahead of time here that would help us to not get confused. In this problem, do we expect Q for the calorimeter to be positive or negative?
Well, since it's a combustion, we expect the Q for the reaction to be negative and Q for the calorimeter to be positive.
So that's another clue that this must be the Q for the reaction, because it's negative. It wouldn't make sense for it to be positive. Now, in this equation, is this Q supposed to represent Q for the calorimeter or Q for the reaction? When we use this equation, is the Q supposed to be the Q of the reaction or the Q for the calorimeter?
Q for the calorimeter?
Yeah, because whose change in temperature are we putting in?
The change for the change in temperature. Oh, that's for the solution.
Which is part of the calorimeter. Since we're putting in the change in temperature for the solution, which is part of the calorimeter, logically, this is the equation that gives us the heat for the calorimeter. So what should I plug in for Q for the calorimeter for this problem?
So Q for the calorimeter should be actually positive.
That's right. That makes a big difference. We're going to get a totally wrong answer if we don't put in a positive number here. So that was an important thing to watch out for. They gave us information about the heat for the reaction, but we need to plug in the heat for the calorimeter in order for this to come out correctly. I guess there's a lot of subtleties on these problems. Okay, so only now are we ready to start doing the algebra. So now what in the next tutoring session in this series, I realized that I had probably made a mistake on this problem. So now I want to go back and fix that mistake. And it has to do with what the student and I were talking about a few minutes earlier in the video. The student had thought that they should set the equation up like this, with one term for the solid portion of the calorimeter and another term for the water. And I tried to convince them that they had made a mistake. But actually in the next tutoring session, I decided that actually probably the student had been right and I had been incorrect. So now I'm going to go back and do it this way. I thought that we should probably leave this term out because the problem didn't give us the specific heat of the water. But actually, the student pointed out to me in the next tutoring session, the problem told us that we have exactly 1,000 grams of water. This problem tells us we have exactly 1,000 grams of water. Why would they tell us that if they didn't want us to include a separate term for the water? So I think that's a good point. So actually now I've changed my mind from what I originally said in the tutoring session. And now I think that actually we should include this separate term for the water, because otherwise, why would they tell us that we have exactly 1,000 grams of water? So what we would expect is that this number here represents the heat that's being absorbed by the solid portions of the calorimeter, plus the water solution. So this term here, this would represent the solid parts of the calorimeter, the reaction vessel, and the thermometer and stuff like that. And this would represent the heat that's absorbed by the water. Originally, I tried to convince the students that when they said calorimeter assembly, that already included the water, but as I've said, now I actually changed my mind. Now I think when they said calorimeter assembly, they just meant the solid parts of the calorimeter assembly. And again, there's two reasons for that. One reason is, again, why would they even bother telling us how much water there is unless we had to include that in the problem? And the other reason is, notice that they told us that this had a heat capacity of 827 joules per degree Kelvin, per degree Celsius. Now, if you go back and you compare that with the heat capacities that we've been given on earlier problems, for example, here's an earlier problem that we did. Notice that this heat capacity is much bigger. 4.881 kilojoules per degree Celsius. Now notice in this case, we definitely knew that this included both the solid portions and the water because the problem specifically told that. And that makes sense because notice that this number is way bigger than this number. So that's what indicates to me that this is only including the solid portions. This number is so much smaller than in this case when they were including the water. That seems to indicate this is only the solid portions and not the water. In fact, if you go back and you look at all the previous examples in the series of videos so far, in all the cases where they were definitely already including the water and the heat capacity, in all those cases, we got fairly large numbers like 4 or 5 or 3 kilojoules. This is the first time where we've seen a much smaller number. This is less than 1 kilojoule. So that's the other clue that it's not including the water. So as I said, I think now we should actually include this term. So here the mass of the water is 1,000 grams. As I said, why would they even tell us this mass if we didn't have to include it? Well, occasionally problems do give you information that's not necessary, but I think the most likely reason here is that they wanted us to use that to solve the problem. Now, they didn't actually tell us the specific heat of the water, and I thought that that was a clue that we don't need to think about that separately. But I guess in reality, people are really expected to know at this point that the specific heat of water is 4.18 joules per gram per degree Celsius. So now I've changed my mind. Even though they didn't tell us the specific heat, they really expect us probably to know that anyway. It was given in the earlier problems anyway. And the temperature here again is changing to T final. From the original temperature. So both the solid portions of the calorimeter assembly and the water would be expected to change temperature by the same amount in equilibrium. So my best guess now is that the problem did mean us to include this term and that the heat capacity here was only the solid parts of the calorimeter assembly. So now we have to do some algebra. $827 times negative 24.98 comes out to be this. $1,000 times 4.18 times TF is 4180 TF. And 1,000 times 4.18 times negative 24.98 is 104,416. Now we collect terms. That's what we get when we collect terms. Then we move this term to the left-hand side. And we divide. So I believe this is the correct answer to the problem. And we can check that that does match our prediction. Because we were predicting that the temperature would rise to more than 24.98. So here's our answer. If you recall, when the student was working on this problem, at first the student was plugging in a negative number for Q for the calorimeter, if you recall, because this number is negative, and the student forgot that this represents the heat of the reaction, whereas the heat of the calorimeter should be positive. So what would have happened if we had kept that mistake? What would have happened if we kept this negative number? Well, if you had put in this negative number, you would have ended up getting a final temperature that's smaller than 24.98. And hopefully that would have alerted us that we'd made a mistake. The whole point of making a prediction is that if your math doesn't come out to match your prediction, there's a good chance that your math was wrong. So if we had mistakenly put in a negative number here for the heat for the calorimeter, we would have gotten something that was a smaller temperature than we started with, and that would have been a signal that we'd made a mistake. In fact, because the reaction is releasing heat, we would expect the calorimeter to be absorbing the heat, and this number should be positive, and then the answer comes out to make sense. By the way, the initial temperature here should also make sense to you, because this is about 25 degrees Celsius, and 25 degrees Celsius is about room temperature. Well, it would make sense that before the reaction, the calorimeter would probably be at room temperature. Okay, so the lesson here, now that I've rethought this problem, the lesson is if the problem tells you the mass of the water, that's a clue that they want you to consider the heat absorbed by the water separately. And they might not actually give you the specific heat of the water because they might expect you to just know that specific heat, at least on homework problems anyway. I think usually on test problems you would be given all the constants that you need, but on homework problems they might expect you to remember that constant from the other homework problems that you've done. And then again, the other clue that this heat capacity did not include the water is that it seems too small for that. Usually when the heat capacity includes both the solid portions and the water portions, it comes out to be like 3 or 4 or 5 kilojoules, whereas this is less than 1 kilojoule, which means that it's probably just the solid portions. Remember that in general, water tends to absorb more heat than other substances. So you can see generally most of the heat capacity comes from the water, as we've seen maybe in other videos. Water tends to absorb a lot of heat, so it would certainly be a big mistake to leave that out. So, as it turned out, what did they mean by this term calorimeter assembly? During the tutoring session, I thought that assembly meant solid portions plus water, but now I've changed my mind, and I think it just means the solid portions of the calorimeter assembly, not including the water, unless they say that specifically. Also, I wanted to remind you of another difficulty we had when we were doing this problem in the tutoring session. If you remember, when we were first doing this problem, I think the student's first instinct was to plug, what did the student try to plug in for Q at the start? At first, the student just tried to plug in 3727, or 3,727,000 for Q. So at first, the student was just trying to plug this number in directly for Q. Let me remind you one more time why that's wrong. What we have to plug in for Q here, well, we need to plug in the actual amount of heat that's absorbed by the calorimeter. Because we're dealing with the actual change in temperature, we want to find what the actual new temperature was, so we need to know the actual amount of heat that was absorbed by the calorimeter. But this number 3727, is this an actual or a hypothetical number? This 3727, is it an actual or a hypothetical number? Well, remember that numbers that are given to you with fractional units are generally hypothetical, and this was given with fractional units. So, did this reaction actually release 3727 kilojoules? Well, no, that's just hypothetical. All this means is if we hypothetically combusted 1 mole of cyclohexanol, then, hypothetically, it would have released 3727 kilojoules. So this is the hypothetical amount of heat that would have been released if we hypothetically combusted 1 mole of cyclohexanol. We eventually found out that, in fact, this was the amount of heat that was actually released, because remember, we weren't actually combusting 1 mole. The 1 mole number here is also hypothetical. How many moles were we actually combusting? 0.00506. This is how much we were actually combusting. And so then this number was the amount of heat that was actually released. So hopefully thinking in terms of those concepts of actual and hypothetical can help you to see why it's wrong to put the 3727 directly into the equation. We need the actual amount of heat, and this is just the hypothetical amount of heat that would have been released if we combusted 1 mole. We needed the actual amount of heat that was actually combusted when we actually combusted 0.00506 moles. I hope that helps you to see why this is the correct number to plug in and not this one. So basically what I'm trying to warn you of is, I guess unfortunately a lot of students have a tendency to think that these mean the same thing. A lot of students think that kilojoules are the same thing as kilojoules per mole. So I'm trying to warn you that that's not true. When a number is given to you in kilojoules, it's generally giving you the actual heat. But if a number is given to you in kilojoules per mole, that's just giving you the hypothetical amount of heat that would have been exchanged if there was hypothetically 1 mole. So these two units don't mean the same thing. You can't plug in kilojoules per mole when you need the actual number of kilojoules. I hope that made some sense, and in the next video in this series, I'm going to go through another analogy that'll hopefully make that clearer, because that seems to be a major source of problems to students with this topic.